Hi, welcome back. This is the second part of the lesson on vector spaces. So remember, we talked a little bit about vector spaces and I was kind of informal about it, but you get the general idea, right? Vector spaces. The idea is functionality and not form. It doesn't matter what it looks like, it's what it does that matters. And in our particular case, it is a question of scaling and adding. These two operations should be very clearly and easily doable, and order should not matter. And there is a zero element. That is an element that does nothing. If you have these properties, then you have a reasonable vector space. What I will suggest is you go on the web. So your homework is to go on the web and find a proper definition for vector space. This should be easy for you to do. Second thing is find an unusual vector space. Something that's rather unique. Okay, so that's as far as vector spaces go. And you're wondering, who cares about vector spaces? Why do I talk about them in general? So what we are interested in is in manipulating things, and it turns out that vector spaces are very useful because they do the basic properties like addition and scaling. So our main idea is to start talking about functionals or functions of vectors. Basic idea for a function is very simple. It's a box. You feed in something and it spits out something. That's how the box works. Okay, this is f. So the input is called x and the output comes out. So if x is an element of a vector space, then we can do interesting things. Okay, so let's look at some casual examples. So for example, we have three-dimensional Euclidean space, and that's a nice Euclidean vector space, and that's a nice one, and vectors there look like ABC, right? And I'm going to put this arrow so that it's easy to see, and ABC are the components of the vector, and you know all this stuff, so I'm not going to bore you with it. So let's look at some functions. So let us say I get f of a b c equal to a squared plus b squared minus c squared, something like that. Okay, so input vector, output number, right? And you're thinking, okay, what's a big deal? We have done this, we know how to do all kinds of things. Now let's look at something more interesting. Suppose my input is itself a function. So remember, set of all functions is a vector space. So now I can do all kinds of things. Suppose I look at the following thing. Given function, input equal to f of x, operation is integral of f of x dx from 0 to 5. So the output will be a number. Okay. Now this integral operation, integral 0 to 5 of something, this one is a function of a vector. More examples. Vector space set of all twice differentiable functions. That means you cannot have step functions and things like that, but it's a twice differentiable functions. So operation ddx of f of x plus f of x whole square. Okay, if I do this, my output will be another function which is in the set of all one differentiable functions. This is a different vector space. Let us call this V2, for example. This will be called V1. There's a more technical name for it, but again, the aim is to get you the idea. I don't want to bore you with the technicalities. I will make you read the technicalities as part of your homework so that you'll gradually be able to get this. Okay, so that's the idea. Okay, and you can see this operation ddx of stuff plus whatever it is squared is my function. So this is where the inputs go. Oops. I don't know what happened. So ddx of stuff plus stuff square. So this is the slot. For a vector, for example, suppose I give you vector ABC, I could do a squared plus b squared plus c squared square root. This is called norm. Technically, this is called 2 norm or Frobenius norm or something like that, but you know, this is what we call norm. And norm is a function of a vector. Okay, so no big deal. We can do all kinds of functions. So a special group, we are very much interested in a special group of functions. And these are called functionals. It looks scary, but it's nothing. So it means input is a vector, output scalar, typically real number. That's it. You know, it's a function for which the input is a vector, output is a scalar. But vector does not mean, don't think line segment, but it means something that satisfies the vector space properties. For example, this is a functional. This is a functional. Can you see that? Input is a vector, which is function of x. Output is a number. Okay. This is not a functional. This ddx operator is not a functional. Why not? Because the input is a vector, but the output is some other vector. It's not a number. Okay. So in this particular case, output is not a number. Right? So that's the idea of a functional. For example, this is a functional. Input is a vector, output is a number. Okay, that's it. As far as we are concerned, this is a very useful functional because we can do all kinds of things with it. So functionals are very useful. I'll look at an interesting example. Vector space set of all twice differentiable okay, my functional f of x, so it will be called f of x equals integral a to b, so these are constants a and b, f of x squared plus df dx cubed minus 3 dx. I just made up something. What do you think? You think it's a functional? Let's see. Input is a function, output is a number. Yeah, it's a functional. How about this? F of x equal to max over x of f of x. Is that a functional or not? What do you think? So, you know, the fancy name for functions on vectors is called operator. So the other name, so the general name for functions generally called operators. Okay, and you can create new kinds of operators and so on very easily, but that, I mean, there is no big deal. It's just a fancy name for functions. Okay, so that's all we are trying to do. You know, you cannot get more general than just saying function, but for whatever reason, because of the slightly different history of all of these things, people started calling them in all kinds of special names. Okay, so why do we care about functionals and functions and all of this stuff? Because functionals are what we are going to use widely in this course. Energy is an example of a functional. Okay, now in thermodynamics, these are called extensive properties. Functionals are called extensive properties. Okay, extensive. Okay, so when you hear extensive property, that means it's a functional from a mathematical point of view. Okay, so the next thing that we're going to talk about is, once you have functions of things, then we want to do calculus. So I want you to understand how mathematics works. Okay, you're wondering what I'm trying to tell you is, mathematics works by being able to do some simple operation which is explicit. After that, it will try to build upon it. It will not try to create more and more new operations. For example, mathematics tells us that what we want to do, we know how to do. So if f of x is x squared, we know how to do df dx. That's easy, no? That's 2x. So if the input is a scalar, then calculus is easy. So single variable calculus is what we build upon. Okay, so our idea is, what if the input is a vector? We only know how to do with scalars. Okay, so what we will try to do is convert vector operations into scalar operations. What do I mean? So the idea is, we are going to do this. We are going to introduce the idea of directional derivative. Okay, the idea is that I have a function of a vector. So example, function of a comma b comma c equals a squared plus b squared minus c squared. That's easy, no? What I want to do is, I'm going to pick another vector, anything that you like. So let us say I'm going to pick, let's go and say I'm going to pick the vector. In our case, I'm going to pick 3, 4, 5. So this represents the direction. Now what I want to say is, go along this. What is the derivative of f of x along 3, 4, 5? And I want you to use only derivative of a single variable calculus. What I mean by that is, I don't want you to talk about gradient and all this stuff here. The only tool you have is single variable calculus. Can you find the directional derivative of this vector? The derivative of f of x, or sorry, f of v along 3, 4, 5. The way to do that is the following. So what I want you to do before you do that is pause, try and see if you can do that yourself. Okay, that's the best way to learn. Once you try something, and it doesn't matter if you got it wrong, just try something, then you have some skin in the game, then you can come back and then you can see what I have done, and then you can figure out why I did what I did. Okay, so our trick is, I am going to create f of v plus epsilon times, so let us call this variable h, like that, right? So how much will that be? That is f of a comma b comma c plus epsilon times 3 comma 4 comma 5, which is f of a plus 3 epsilon, b plus 4 epsilon, c plus 5 epsilon. So far you have done nothing, no? So then go substitute there. This will be a plus 3 epsilon squared plus b plus 4 epsilon squared plus, minus c plus 5 epsilon squared. This is some new function of epsilon. Can you see that? This is g of epsilon. So what did I achieve by doing all of this? I converted the problem into a single variable. That's what I was trying to do. Right? Now I'm going to do dg d epsilon, and I'm going to put epsilon equal to 0. This will be called the directional derivative. Let's see how much I will get. So 2a plus 3 epsilon times 3 plus 2b plus 4 epsilon times 4 minus 2c plus 5 epsilon times 5, which is equal to, and I'm going to put epsilon equal to 0. So then I'll get 6a plus 8b minus 10c. You can try any other method, you'll get the same answer. Right? This will be called derivative of f in the direction of h. H is that, this is v. Okay, technically it should be at a comma b comma c, at that point. So derivative of f in the direction of h at a, b, c. So this tells you where I am evaluating the derivative, this tells you in which direction, and all it requires for you to be able to do is single variable calculus. And I am here to tell you that the entire stuff about variational calculus is just nothing but single variable. It is just calculating directional derivative. If you know how to do this, and if you know how to do this operation completely, you can actually do it very, very fast. What happens is somewhat tedious, so we take some shortcuts, but otherwise it's just this idea. Okay, so our most important concept here is there. So we have covered two important concepts. I'm sorry. One is what is meant by a functional, which is just a function of a vector whose input is a vector and whose output is a number. That's all a functional means. That's item number one. Item number two, we talked about what is meant by directional derivative. The technical name for this, if you want to what is that, impress your friends and probably get yourself the name of total geek, the name for a directional derivative is Gateaux derivative. Okay, so you're wondering, okay, so what's the big deal? I did directional derivative, so how does it matter? Let's try something that's kind of interesting. Okay, so now let us try this. F of x equals integral f of x squared plus df dx of x 0 to 1. So I want to find directional derivative of f of x in the direction of h of x, which you think, what the heck do I mean by direction? Don't worry about it. We are just going to do the formal calculation. Okay, formally what this means is that first, step 1, create f of x plus epsilon h of x. Can you do that? Pause it, write down this expression, and then come and see what I have. Okay, very good. Did you pause it? Did you write down your version? Then come and see what I have. What I have is the following: f of x plus epsilon h of x equals integral 0 to 1 f plus epsilon h whole square plus f prime plus epsilon h prime squared dx. All I did was, wherever I saw f of x, I replaced with f plus epsilon h. So far so good. Now this is some function g of epsilon. Can you see that? Because all the x is integrated out. So step 2, differentiate with respect to epsilon. That's easy. TD epsilon integral 0 to 1 of f plus epsilon h whole squared plus f prime plus epsilon h prime whole square dx equals, again pause, you do it, then come and see what I got. That's better than watching me do it. You cannot build muscles by watching an exercise video. Okay, I know how to do it, and even if I get it wrong, there's nothing you can do. I got tenure. Okay, but you guys have to learn how to do this right. So I'm going to show you. This turns out to be integral 0 to 1 2 f plus epsilon h times h plus 2 f prime plus epsilon h prime times h prime dx. That was easy. Now I'm going to set step 3, put epsilon equal to 0. That's easy. Integral 0 to 1 2 f h plus 2 f prime h prime dx. If you've taken a finite elements class, or if you've taken any of these things, you would recognize this kind of stuff. This is very closely related to this idea called the weak form. Okay, but we are coming at it from a purely mathematical point of view. That is, I've started with a functional and I just took the derivative in the direction of some function. Okay, now there's one more step. Step 4, integrate by parts until the direction h of x is not differentiated. The problem is this is h, no? This is h prime. I don't want h prime. I just want to replace it with h. So what I'm going to do is I'm going to integrate this by parts. We know how to do that, right? Integral 0 to 1 2 f prime h prime dx equals integral x equal to 0 to 1 2 f prime dh prime. So dh, you can do whichever way you like. I'm just doing it as u dv is uv minus v du. So that is equal to f prime h between the limits x equal to 0 and x equal to 1 2 times minus integral f double prime h dx. That's h df prime. So that will give you that. Sorry, I'm missing it too. So what did I get? I got this integral 0 to 1 2 f h minus 2 f double prime h dx plus 2 f prime h x equal to 0 to x equal to 1. This is a boundary. This thing is called the natural boundary condition. This is the Volterra derivative. Okay, the total, this is Gateaux derivative. Sorry, I shouldn't really call this the Volterra derivative. I should be a little bit more careful. It's a little bit sloppier. This is equal to integral 0 to 1 2f minus 2f double prime h dx plus this thing, the coefficient of h in this equation is called the Volterra derivative. So this is a 4-step process. Step 1, step 2, step 3, step 4. If you get good at doing this, you will go very far. Okay. Now there is a shortcut for doing this, and that's what I'm going to show you now. Okay, this is a shortcut. The shortcut is based on the use of what is called the delta notation. Works in the following way. So I'm going to write f of x equals integral 0 to 1 f of x squared plus f prime of x squared. I'm going to do a small variation of f of x. Okay, this is represented as delta f of x. That is, if I change this internal thing f of x by a little bit, what will happen? Well, I'm going to do like a Taylor series expansion. So this will become 2f delta f plus 2f prime delta f prime. Right? This is what I would do if it is an ordinary function. You know what I mean? Now what I'm going to do is integrate by parts. This is equal to integral 0 to 1 2f delta f minus 2f double prime delta f plus 2f delta f, sorry, f prime delta f between the limits x equal to 0, x equal to 1. And again this will be integral 0 to 1 2f minus 2f double prime delta f dx. This is again the Volterra derivative. I want you to understand, look, I got exactly the same answer. If you compare this guy with this guy, I want you to see, plus all this stuff, I want you to see I'm getting exactly the same thing. 2f minus 2f double prime. Where is that here? 2f minus 2f double prime. Very good. Let's see if I can put both of them in the same screen. Yeah, there you go. This h has become delta f here. This natural boundary condition is here. Can you see that? It's exactly the same thing. So if you are used to doing variations like this is nothing but our usual idea of directional derivative. There is no difference. The directional derivative is the proper way to do it. The variational method, putting the delta, is a shortcut. Many of you may be more comfortable with one or the other. I don't care which one you use. The shortcut, many people are very comfortable with it. If you are not comfortable with it, please pay attention. The main thing is to do it in a two-step process. First one, do the variation. Second one, integrate by parts. So I want you to tattoo that into your brain. So first one, do the variation. Second one, integrate by parts. So if you're doing the other way, which is by using epsilon times h, first one, do the derivative with respect to epsilon, put epsilon equal to 0, and then integrate by parts. That's how it works. Okay, with that we are done.